All right, folks, we're going to talk about power in this video, which is really just the last thing in Unit 3 because we packed so much into our previous videos with all the work and energy and conservation and systems and all of that. Now, power is a little more standalone. Power is sort of its own topic. It connects absolutely to work and change in energy, but it can sort of just be addressed with its own equations and its own definition a little bit more separate from energy types and all of that. But it is connected to work. So, to illustrate the idea of power, before we write a definition for it, below here, I'm going to do a bit of an example to talk through when we say power or powerful, when we talk about how much power something has in the real world here. I'm going to use the examples of cars or vehicles, and hopefully that'll connect to then our physics definition. All right, so we're gonna have two cars or two vehicles. We'll have one is, well, I'll just have this be my car, which is a trusty Toyota Corolla. I don't claim to be very good at drawing cars, but here's the Corolla. Not particularly known for its power, but it gets me where I need to go. The other vehicle we're gonna try and make it maybe a little more sleek looking. All right. We'll have this be, I don't know, a Lamborghini. We'll say it's a Lambo. Pretty expensive car, pretty powerful. I mean, I'm not a huge car person, but comparing the two, my Toyota Corolla doesn't nearly have as much power as a Lamborghini. All right, so we're going to say that both these cars are going to start at zero. They're going to start at like a stoplight or something like that. So V initial equals 0 for both, which means there's no kinetic energy, right? Kinetic energy of motion means if you're moving, you have kinetic energy, but if you're sitting still and not moving, no kinetic energy for either. All right, and from that stoplight, once the light turns green, we're going to say we're like getting on the highway, and both cars are going to try to go from 0 to 60 or 70 miles an hour. And this is going to illustrate, of course, power, because what happens is, well, we'll look at them both as they go from 0 to, I don't know the conversion to meters per second, but that's okay. We're not really going to be doing any math here. So we'll say the V final for both of them is 60 miles an hour. We would want that in meters per second if we were doing any equations in math, but we're not going to go quite that far here where we're not calculating anything. All right, and let's say they do this by going from 0 to 60, and their displacement. So by the end of this is the end of the exit ramp, and they're going to be getting on the highway. So by the time they're getting on the highway, both cars want to be going 60 miles an hour. So their displacement is the same. This is also the same final velocity for both. They will both reach a final velocity of 60, and the displacement delta x, however far it is from the stoplight all the way to the end of the entrance ramp, as I attempt to draw a straight line, more or less, is also the same for both. So what's different between these cars? We've claimed that the Lamborghini is more powerful, but so far they've both gone from the same initial velocity to the same final velocity over the same displacement. So what is it that's different? Well, the key difference for a powerful car like a Lamborghini versus something like a Toyota Corolla is the time it takes. Now, we could also reference work here real quick to say they both change kinetic energy. They go from no kinetic energy at the beginning to some amount of kinetic energy at the end. And for those purposes, we'll just say we're going to assume, which this is certainly not true, but to make our problem a little more simple here, we're going to assume they're roughly the same mass. They're probably not too far apart. Maybe they are, but we're going to assume the same mass for both. What that means is our kinetic energy equation, because kinetic energy is simply equal to 1/2 mv squared. By the time they both reach the end of the exit ramp, they have the same kinetic final for their energy. And in terms of work, because the change in kinetic energy they experience, both going from 0 miles per hour, no kinetic energy, both ending with the same amount of kinetic energy with the same mass. Again, we're assuming that, and the same velocity of 60 miles an hour. The change in kinetic energy, which is equal to work, that's our work energy theorem that says whenever work is done, there's a change in kinetic energy. We could talk about the force of the engines, right? We know force times displacement times cosine theta is work, force acting parallel to displacement. So that work done by the force of the engines over a displacement of however far the entrance ramp is, that amount of changing kinetic energy and the amount of work done, because they both start at 0 and they both end with that same amount of kinetic energy, the work done is actually identical for both. Assuming that they were over the same displacement. Now, there's some differences here. We're glossing over a little bit. But the main illustration that I want to make, the key difference here, the really important thing about what's different between the Lambo and the Corolla, right? Because everything else was pretty much the same, is that time, delta t, is significantly less for the Lamborghini. Okay, so that's what we're gonna key in on for our definition of power. So power is defined as the rate at which work is done. And that's it. Um, so the rate at which work is done means, sure, both cars could do the same amount of work if they both start at 0 kinetic energy and they both end up with the same amount of kinetic energy as each other. Then that change in kinetic energy, which is work, would be the same for both. But even though both cars could do the same amount of work, the rate at which that is done, or the time it takes to do that work, is a much higher rate of work and a much smaller time for the Lamborghini because it is much more powerful. So let's get through the variable and the units and equation. Capital P is the variable for power. That makes sense. It is a scalar, not a vector. So like energy and work, it doesn't have a direction, no direction on power. And before we get to units, let's go ahead and look at the equation, because the equation is going to help us figure out what the units are. To find power, it is simply equal to work over time. As we said, it's the rate at which work is done. If we think back to something like acceleration, acceleration is the rate of change of velocity, or the rate at which velocity changes. So we had delta V over delta T. It's okay, something's changing, something's happening. In this case, it's the kinetic energy changing when work is done. Okay, at what rate is that happening? That means how long does it take for this changing kinetic energy to occur? Just like acceleration is like, well, how long does it take for you to speed up or slow down, right? That goes into the equation. Change in velocity over time gives you acceleration. Work over time gives you power. So it's related to how long does it take, what is the rate at which work is done. Work over time gives you power. It's pretty simple. We'll talk about another alternate equation in just a second for that down below, but that's our starting point. All right, so what units does that leave us with? Well, the units are they're joules per second. That's one way that you could describe them. And to be entirely honest with you, I'm blanking on the word for them. So we're just gonna look up the units of power. It happens to even your teachers. Um, watts. There we go. I must be very tired. Um, so watts, which slipped my brain for a moment there. You can use a capital W for those units, and they are equal to we could say watts or joules per second, right? Energy is in joules. Um, Work is in joules, time is in seconds. So joules per second are a valid unit for power. We usually do write that as watts, though. We don't tend to say joules per second. We usually just go with watts. Okay. So it's the rate at which work is done. It's found by taking work divided by time. And the whole idea of power or something being powerful is it causes a change in energy through work being done. And if it's really powerful, well, one of two things could happen. You could either do a lot of work, right? And there's actually a cool comparison here between like trucks and like sports cars. So something like a Lamborghini or a really fast car, the key there is the time, not necessarily the work being done. So the power of a really fast, speedy car comes from the fact that it speeds up super quickly, right? The work that's done to go from no kinetic energy to having a lot of kinetic energy, that work happens in a short period of time. But something like a truck, right? You got a really, really big, powerful truck. Sure, it could do a decent job at speeding up. It might not be the worst 0 to 60 time, but that truck really its power doesn't primarily come from the time, even though it would be okay at speeding up, probably even good at it. But the amount of work done by a really powerful truck is really big. Like picture, a truck towing some massive object, something that takes a ton of force to move. That amount of work, just the raw amount of work being done by something like a really big, powerful truck, that's where that power kind of comes from. So, interestingly, we could say, sure, you could make the time really short. If time gets small, power goes up, like a fast car. Or if just the amount of work is really, really large, that also would mean your power is then bigger. So, there's a couple ways you could think about that, right? But regardless, if something is powerful, it either does a lot of work in whatever time is going by, or it has a really short period of time in which it does that work. All right. And that's pretty much it. This is for the basics of power. This is it. It's like, well, whenever work happens, could be friction doing work. So they'll talk about like power dissipated by friction. That word dissipated gets thrown around a lot with friction because the heat and the sound goes off and dissipates and disperses into the surrounding air and environment. Um, but yeah, they'll talk about it with friction. You could say the work done by applied force, the work done by gravity. All those could, in theory, relate to power because you could say what amount of time does it take for that work to be done and what is the rate at which that work is done. Okay, so that's the basics of it. You'll see it tied to work and time and those changes in energy that happen when work is done. So the work energy theorem is an important thing to remember when it comes to power because we could find work or we could find the change in kinetic energy and then just divide by time to get power. Now, there's an alternate equation here. There's another way we could find power. And we're going to start with the power equation that we had, and we're going to work with it to get something else. So we had work over time, but work, we have the work equation, which is absolute value force times absolute value displacement times cosine of theta. Divide that by time, because this is still work in the numerator. We just replaced work with force displacement cosine theta. That is the equation to find work. So all of this in the numerator is still work, same exact equation, just dividing by time again. Now, one thing we could notice is Well, displacement over time, delta x over delta t, way back in unit 1, that was our average velocity. So we're going to write this alternate equation below, and then we're going to specify a couple things about it. The way that I believe it should show up on your equation sheet is force times velocity. Now, that is a simple equation, but there's a few things we kind of left out from what we had up here. The first is displacement over time is technically an average velocity. So this needs to either be one of two things. It could either be, we'll say it needs to either be constant velocity, in which case, if the velocity is constant, the average velocity, if something goes three meters per second and then it's still going 3 meters per second and then it's still going 3 meters per second, the average velocity there is just 3. If the constant velocity, if it remains the same speed, the same velocity the whole time, then the average is just however fast that is. So either we could have a constant velocity, or we could use the average here. If you have a way to find, hey, this is the average velocity of this object, then you're good to go. So the two options here for this equation is you either need to use a constant velocity, or you need to know from this problem, I read the problem and it said it moves at constant velocity. Okay, I'm good to go. I can use the velocity times the force to get power. Or the other option is from the problem, you're able to determine, oh, I can get the average velocity. Here's the average velocity of this object, whether it's a number or just the variables for average velocity. So either a constant velocity or an average velocity times the force. And then the last piece is this force. If we look at the cosine theta, right? If the force was acting opposite to the velocity, we'd expect a negative work. And that would actually work okay here. That would be fine, because if the force is positive, like to the left, and the velocity is also, or sorry, I guess to the right is usually positive. So we'll say if the force is positive to the right, for example, and if the velocity is positive, which would then also be to the right, positive times positive is positive. So quick note here with positive negative, you can get negative. You could in theory get negative power, but we're probably not gonna encounter situations where you're really gonna have to work with negative power. So really the only thing we need to note here is not necessarily be worried about, well, is the force to the right or left and the velocity to the right or left. Instead, we're just going to say this force needs to act parallel to the displacement. So that whether that force is in the same direction as the displacement and the velocity, or opposite. Also, we could just make a quick note here. If your object moves to the right, your displacement is to the right, positive, and so is your velocity, because that's the direction it's moving. If your object moves to the left, its displacement is negative or to the left, and so is its velocity. So from unit 1, hopefully we know this as well, but displacement and velocity are always going to be, well, in the same direction, unless you're looking at a longer period of time, and then it changes its velocity, and it was going to the right, and then it goes to the left, and there could be more involved things. But we're not going to get into the weeds with any of that. We're just going to say if an object's moving and it has either a constant velocity, or we could find the average, and we know that that force acts parallel to that displacement or velocity, then we can use this equation. So there's those limitations on it, right? But be on the lookout for if your AP question starts telling you some things about force, and then it gives you some information that you could use to find or look at velocity, keep this in mind as a way to find power. It's an alternate equation or a way to find power, because work over time with the work equation gives us delta x over delta t, which is our average velocity times force to give us power. So provided that we sort of meet those requirements of the parallel force with the velocity and then constant velocity or average, then we can use this equation. It's not a ton of problems necessarily, but it could pop up in some of your power problems. Yeah, so anytime there's power, we just want to think about work being done, whether that's a change in energy or the force and the displacement and cosine theta. And then we can use either work over time or force times velocity sometimes. Yeah. And yeah, you can obviously use this to solve for work as well. So if you know the power and the time, you could isolate and solve for work also. Um, yeah, a pretty simple equation overall. Got a couple different versions of it, but nothing too crazy to work with. Most of the power problems are not too tricky. You just want to consider like if they're asking for the power output of like a person's applied force, just keep in mind that you don't want to incorporate friction into that. For example, if someone pulls a box across the ground and they ask you how much power output is the person putting out, well, you don't want to look at other things like friction doing work or gravity doing work or something else. You would just read the problem and say, oh, they only want me to look at the power from the person. Well, then I'll just look at the work done by the person. On the other hand, they might say, like, what's the overall like power based on all the various forces that are doing work and things like that. In that case, you'd say, well, maybe the person does for our equation here. You'd say, oh, the person does 200 joules of work, but friction does negative 50 joules of work. So the total work would be 200 minus 50, and you'd get a work of 150 joules that you would use in your equation to find the overall power output in that situation. So just keep your eyes open for things like, are they asking me about the work for this particular force, or are they asking me about overall? Um, yeah, so force, displacement, time, velocity with force sometimes, and then energy is a thing to keep in mind because the change in kinetic energy is always equal to work. So you can use that to help find your power in a problem. Okay, well, I'm not going to say much more about power because it's fairly short. We'll do examples in class, so we'll go through some problems and see, like, okay, how do we use this power equation? Where does it show up? And which problems? And you'll get a chance to practice some of those yourselves. But that pretty much wraps it up. There's a few odds and ends things that we might talk about some specifics of something in class, or we'll do wrap up summary of Unit 3. But a lot of Unit 3 is like taking these individual pieces that we covered in a fairly short amount of videos overall, but it's more about applying work systems, open and close, energy changes, types of energy, conservation of energy, external work, power. All these things just get applied to specific problems, and it's just figuring out, okay, is this a conservation of energy problem, or do I need to use my work equation, work energy theorem, power, um, which one applies to specific problems. Alrighty, well, we'll leave it there for the video, a fairly short one this time around. And don't forget, you can ask any questions. Feel free to put those in the Padlet on Schoology or bring them to class. And we will, yeah, we'll see you in class.